Hi, Year 10 and 11. So we're still working on example 32. This video is, I think, video 10, and it will follow on from directly from the last video where we'd halfway gotten through example 32 here, which I'll quickly remind us about what happened. In example 32, there was a graph, and it was the question was slightly different to the one there, but the graph was the same, where a patient was admitted into hospital with a temperature, and there's the T for temperature, and temperature was monitored over a time T, so T is on the bottom. So midnight was time 0. After 3 hours, it was 3 a.m. So for up to 9 hours later, it was 9 a.m. And we were looking at the shape of the graph. We were looking at the... If we have a look earlier, what we were looking at here. Looking at where the temperature was increasing most rapidly and then decreasing most rapidly, and where it was stationary. So we've done A, B, and C, and we're up to sketching the graph of the rate, dt, at which the temperature is changing. So dt is the first derivative. We're taking the derivative and we're looking at the tangents. Okay, here's our function. We have not, however, been given an equation of that function. So we're going to have to go back and have a look at our rules in order to look at what is happening and being able to draw that graph. So these are the things we want to have a look at here in order to draw our graph for the function, or our graph for dt for the function that's been given. So remembering these three things, when the tangent has a 0 gradient, we have a curve that has a turning point or a stationary point, and that's when our first derivative at that point is equal to 0. When our curve is increasing, or our first derivative at that point is greater than 0, we say that dy dx is increasing. Okay, or our curve is increasing there. When the curve is decreasing, we're having the first derivative, or the gradient of the tangent, at a point A being less than 0. So they're the three things we are going to need to use in order to answer the question. So I'm jumping between a couple of pages here. Same question. So this was our graph. This is our function. We want to find dt. I'm going to go back to where I've got it on the OneNote, because I've actually drawn the little gradients of the tangents on there. So it's down the bottom in rates of change. There we are. So I redrew that graph, remember, from question B, I think it was, and we drew the gradient of the tangents at different points, and we found out that the maximum that it was increasing, or the wording that we used in the question, was when was her temperature increasing most rapidly and when was it decreasing most rapidly. Well, the temperature was increasing most rapidly at time equals 0, or at midnight, because that's where the slope of our tangent was the greatest. So that is the greatest point of our dt. So I'm going to redraw this graph underneath and try and make it fit in nicely. So if I redraw the axis that we've got there, and that's our time, and if this is dt, we know that the maximum dt value happened at time equals 0 up here. Okay, because the maximum slope of that tangent happened at time equals 0. And then it was still increasing, but not at as much a rate until we got up to 3. And that's when our dt, or our first derivative, was 0. And that's where our stationary point happens. But that means that our value at time equals 3, or 3 o'clock in the morning, of dt is 0. We'll line up these other values here. Okay, then we got to think, well, what happened to our tangents there? Okay, we drew tangents all along the curve while it was decreasing, and the maximum decreasing happened at time equaled 6, so 6 in the morning, because that was the steepest tangent at that point there. The other ones were not quite as steep when we drew them along there. So that was our steepest tangent. So that means the biggest value in the negative direction is going to be at this point here. So we're basically having a graph that comes down here, and then once it gets to 6, this value of our tangent is going to become less not less, sorry, it's going to be a lot, the gradient's going to be smaller. So we're going to actually be coming up this way until we get up to 9. And then what happens at 9? It tends to look like that the gradient is flattening out. Okay, so we're going to kind of look and go up there like that. So that would be a graph of dt dt. And this is a graph of our function. And that answers the question D. Sketch the graph of the rate dt dt which the temperature is changing. Now that one's quite a hard question, and that's going to take a little bit of practice, I think. Let's look at E. E's saying, when was the rate of change decreasing and when was it increasing? So to answer that question, we need to have a look at the rate of change graph, which is the graph that we've just drawn, the dt dt graph. When was the rate of change decreasing and when was it increasing? So our rate of change, and that's our dt dt, so the rate of change of the temperature, is actually decreasing in this area here. So it's decreasing between time is 0 and time being 6. So we could probably write that like that. So it's decreasing in that range. You can see the graph, it's going downwards. When we get to 6, it starts to increase again. So in that area there, 6 onwards, and we don't know how far we're measuring it in terms of time, so we don't have a finite value to pop at the end here. So I'm going to say that when time is greater than 6, we are increasing. And over here, we were decreasing. And that's our dt dt, or the rate of change in the temperature.